Moving forward in Chapter 6, we now want to start applying some of these ideas about electron configurations to some of the chemical ideas we had discussed before. We're going to start with ions. And so we go back to Chapter 2. We talked about ions, that we know these are atoms that have gained or lost electrons and are no longer neutral. And so we have cations, which are positive, which means those are atoms that have lost electrons, and anions are negative, which means they've gained electrons. So because these electrons are coming and going, we want to look then at the electron configuration of these ions, right? If they still have numbers of electrons, we can put them in places. So if we have a cation, when you remove those electrons, so say you go from Na to Na+, that's lost one electron, we know that the electron that's removed has been taken out of the highest energy state. So if we just look, we would see, just on the configuration, sodium, it's 3s1, right? That 1 that's the highest energy, it's going to be taken out. Similarly, we can see really clearly that it's, the highest energy in that noble gas configuration, and that electron is going to be removed. So in the Na+, you just don't have that. There's one fewer electron. So there's where you hit the point of where you're out of electrons, filling shells happens earlier. When you do an anion, say of going from oxygen to O2-, we can see that we just add those electrons based on the Aufbau principle, right? Here, we stopped with 4. We have 2 more electrons based on it being 2-, and so that's why we get up to 6. In this case, you can, if we look at the noble gas, we can see we swapped from helium plusum to just matching neon, right? So now we have these extra electrons to match neon. And so when we look at these, sodium going to Na+, and oxygen going to O2- have actually changed to the point where they match neon, right? Both of them in the ionic form have the same electron configuration as neon. And the term for that is that they are isoelectronic. That means they have the same number of electrons in the same types of subshells. So neon atoms, sodium plus cations, and O2- anions all have the same electron configuration. They're all isoelectronic. Iso always means same. So isoelectronic, same electrons. So if we return to the idea of predicting ionic charges, we can start to understand some of what we talked about before. For example, noble gases, we said didn't form ions, whereas the nonmetals, things in this region on the periodic table, tended to form anions. They gain a couple more electrons. Whereas on the other side, your metals over here lose a couple of electrons. And we were able to predict how many based on the number of columns away from being a noble gas that atom was. How many extra electrons or how many fewer electrons did it have relative to what a noble gas would have, which doesn't form any sorts of ions. And so if we look at, for example, just going along, this is nitrogen has 7 electrons up to magnesium with 12. If we look at all of their electron configurations, neon is stable. Neon is a noble gas. Noble gases are characterized by not reacting. So they don't react means they don't do chemistry, meaning that the electrons are stable in the situation or in the state that they're currently in. So everything else wants to change in order to look like neon. So nitrogen is sitting at only 3 electrons. It needs to get, if it wants to look like neon, there need to be 6 electrons in that 2p subshell. So it needs to gain exactly 3 electrons. So we expect that nitrogen is going to form an anion with a charge of -3. And this is exactly what we predict and what we see. Similarly, oxygen needs 2, it goes to 2-. Fluorine would want to gain 1 extra. We can see on the other hand, at the bottom here, sodium and magnesium have too many electrons. They're just a little bit past stable. But if they lost 1 or 2 electrons respectively, they would match neon and have that stable number of electrons that neon has. So if we look at all of these ions, anions for nitrogen, oxygen, fluorine, neon atom, and then cations of sodium and magnesium, they all have the same electron configuration. They are all isoelectronic. This is in general true. Stable electron configurations look like noble gases. That's why we picked noble gases for the configurations of that notation. And this idea of stability, we can understand that noble gases, the reason why they're special is that their subshells are full, right? If we look here, it is 2s2, 2p6. That entire shell is full of electrons. There are no unpaired electrons. All the orbitals are full. Everything is looking good. These 8 valence electrons corresponds to a stable configuration. All of the noble gases have 8 valence electrons, so they all line up as they have, 2s2, 2p2 for neon, but 3s2, 3p6 for argon, krypton's below that in 4, xenon's below that in 5, and it keeps going. And so these ideas, these are noble gases, so they're going to be stable with those 8 electrons. So these octet is what we usually call that. 8 valence electrons just corresponds to having a full valence. That's what's stable. All right, so let's look at some examples of coming up with noble gas configuration of ions that are likely for each of these atoms to form. So I got chlorine, TL, that's TL, not Ti. TL is thallium, Xe is xenon, and then Ti 2+. Ti is a transition metal, so I have to tell you that it's going to be 2+. So in each of these cases, you want to know what the most likely ion for each to form is. Before, rely on that information that we have previously. We learned things about atoms, right? Which ions they were going to form, those sorts of things. And so we can use that information to our benefit to kind of figure out then what the electron configuration would look like. We generally don't want to start with the electron configuration because we can figure out a neutral atom based on where it is in the periodic table. If we know what kind of ion it is, then we can make changes to that neutral electron configuration. First, let's take a look at chlorine. So you see chlorine is right here on the periodic table. And we can use the information, we already know that based on where something is on the periodic table, we can predict its charge. Chlorine is in group 7a, so it's going to become a -1 ion. We learned that before just being because, but now we can see it's because chlorine has 7 valence electrons. Gaining 1 more brings it up to 8. So chlorine as an atom looks like neon, 3s2, 3p5. When it gains that 1 extra electron, we can see it goes right there, gains the 1 extra electron, and now it looks like argon. We can also see that in terms of working through this, we maybe don't have to go through all of the work of identifying what the electron configuration of the atom was. We know the motivation for chlorine to become the Cl1- is to look like that nearest noble gas, to look like argon. And so we can predict the configuration is just going to be argon. And any of those, most all of the atoms that we learned how to predict charges for at the very beginning of the semester, their ions are going to have just noble gas configurations. Because all of those rules, those are the hard and fast rules. When an atom can reach a noble gas configuration, that's what it's going to do. Okay, so Xe is right here. Because it's a noble gas, it doesn't form ions. It just goes to Xe, which means the electron configuration stays Xe. The motivation of all of these atoms when they're forming ions is to become more stable. And noble gases already are. That is already a stable electron configuration. Everything else are trying to become a noble gas. That's why noble gases don't change. They have that full valence. It's 2 electrons in the S, 6 electrons in the P. Nothing, everything's full. There's no kind of wiggle room. And so that's the stable configuration. Strontium, you can see, is right here. That is in column 2A, right there. So we know it's going to lose electrons. It's going to lose 2 electrons, become strontium 2+. That's because as an atom, it has these 2 valence electrons. So it just loses both of those, and all that you're left with is the krypton, right? There's the 38. If you lost 1, it'd be 37. If you lost 2, 36. The exact same as krypton. Tellurium, Te, right there. That's going to go to 2- because we're in column 6A, so we would expect it 1, 2 more, so it needs to gain those 2 electrons. We can see that those 2 electrons would give it, it currently has 4, plus 2 more would give it the 6 p electrons that we expect for a noble gas. It just becomes xenon. Isoelectronic with xenon. Participation 623, question 1. Write the noble gas configuration of the most likely ion for each of the following atom types, Li, C, Br, and He. This is the first question on participation 623, due Tuesday, June 23rd at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, write the noble gas configuration of the most likely ion for each of the following atom types. It's lithium, carbon, bromine, and helium. Okay, we had our first participation question in this video. Participation 623 due on Tuesday the 23rd. Also on Tuesday, periodic trends lab, pre-lab and notebook due at 9 a.m. Both are due Wednesday. Also on Wednesday, I'm going to make sure you complete that lab technique presentation questionnaire. Just what topic are you going to do, and what topic are you going to do, and when do you want to present? And then on Thursday, we'll have exam 3 first, and then we'll go do the lab practical afterwards, and then lecture module 8 to end the week. We are going to finish chapter 6, get into chapter 7 a little bit. This will be the end of the material on exam 3 for Thursday. If you have any questions about anything, if you want to meet before the exam, talk about anything, let me know. Otherwise, see you in the rest of the video.